Today we are demonstrating Xilinx's SDAccel development environment for acceleration. SDAccel combines the industry's first architecturally optimizing compiler supporting any combination of OpenCL, C and C++ kernels, along with libraries and development boards for the first complete CPU-GPU-like development and runtime experience for FPGAs. This video will show how software developers can program and accelerate OpenCL, C and C++ applications. SDAccel targets x86-64 platforms with PCIe-based FPGA accelerator cards from an ecosystem of systems providers such as Alpha Data, Pico Computing, and Convey Computer. The demonstration today will use a standard x86-64 workstation containing an Alpha Data ADM-PCIE-7V3 accelerator. This is a half-length, low-profile PCIe Gen 3 accelerator card designed for both the form factor and power limitations of data center deployment. The card contains a Virtex 7 690T FPGA, 2 independent DDR3 channels, and networking connectivity. Let's begin by looking at how a standard OpenCL application is accelerated using a Smith-Waterman algorithm that performs local sequence alignments for genes and proteins. Let's look at the host code which runs on the x86-64 CPU. At the beginning of execution, the application calls the OpenCL API's CLGet platform IDs and CLCreate context to query the platform and create an execution context reserving the FPGA accelerator device. Next, the single OpenCL region on the FPGA card must be configured with the accelerator for the Smith-Waterman kernel. The output of kernel compilation, an OpenCL program binary file or XCL bin file, is loaded into memory, and reconfiguration of the OpenCL region occurs when the CLCreate program with binary API is called. After reconfiguration, DDR memory on the card is reserved with CLCreate buffer. Data is copied with CLRead and CLWrite buffer, and the accelerator is started with CLNQND range. Now let's look at the kernel code. The Smith-Waterman kernel is written in OpenCL C. Here we see the kernel keyword and workgroup sizing attributes. All the standard OpenCL C host code constructs in the embedded profile are supported. In the middle of the code, we see a Xilinx vendor extension attribute, XCL pipeline loop, which directs the compiler to generate a deep pipelined implementation of the inner loop, with all stages running in parallel in hardware, a very common pattern in FPGA-based accelerators. This attribute is part of a suite of our architectural compiler optimizations and extensions which enables the programmer to explore rich design space of efficiency optimizations. Now let's compile the kernels. SDAccel supports 2 flows which allow us to verify the correctness of our design and optimize performance before generating hardware. SDAccel provides a CPU emulation flow in which the kernels are compiled into an XCL bin file containing native x86-64 code. This is a very fast compile, enabling the developer to verify the correctness of their algorithm and perform high-level algorithmic optimization with very fast software compile cycles. Here, I'm running the CPU emulation flow for Smith-Waterman with SDAccel. The application is compiled to x86 and run, outputting a self-check to the display. Let's look at the system estimation report, which tells us the size and performance of the kernels in hardware. The system estimate can determine overall throughput, subject to memory bandwidth requirements, and can determine the overall FPGA area consumed by each kernel within 10% accuracy. SDAccel provides a hardware emulation flow to allow further verification and performance optimization before running in hardware. This flow compiles the kernels into an XCL bin file containing a fully cycle-accurate model of the accelerator hardware. This enables developers of high-assurance applications to observe the cycle-by-cycle behavior of the accelerator internals before hardware. Here we see the output from hardware emulation is equivalent to software emulation. Finally, we compile the accelerator to hardware. The first step of compilation is SDAccel's architecturally optimizing compiler, which automatically applies a range of basic and advanced optimizations to the kernel code. Some of these automatic optimizations significantly improve overall application efficiency. For example, SDAccel compiler's data flow pipelining can pipeline multiple functions instead of being limited to optimizing a single function. The compiler's memory optimizations can greatly improve a function's efficiency, so that you can fit more functions into the FPGA. The kernel accelerators are then integrated and a partial bit stream is generated for the target OpenCL region and packaged into an XCL bin binary file. As you can see, it's just finished running on the FPGA. Now I'll describe some of the features unique to SDAccel. SDAccel provides the first CPU-GPU runtime experience on FPGAs. SDAccel keeps the system functional during kernel updates with the only FPGA-based dynamic reconfigurable capability that can load new hardware accelerator kernels, similar to the abilities of CPU-GPU accelerators, while keeping critical system interfaces and functions such as memory, Ethernet, PCIe, and performance monitors live. SDAccel provides C-based FPGA-optimized libraries to enable CPU-GPU developers to easily migrate their applications to FPGAs, whilst maintaining and reusing their OpenCL C and C++ code in a familiar workflow. These libraries include low-level math libraries and higher productivity libraries, such as BLAS, OpenCV, and DSP libraries. They're written in C++ as opposed to RTL, so they can be parameterized from software functions and can be used exactly as written during all development and debugging phases. I'll demonstrate these features with code snippets from a computer vision application written by our alliance partner Orvis Systems to accelerate high-definition rate video processing for automotive lane detection. In addition to OpenCL, SDAccel allows developers to write kernels in C++. The static subset of C++ is supported, common to C++ usage in highly optimized application domains, such as graphics programming. SDAccel fully supports inheritance and templates, enabling higher developer productivity through object-oriented design patterns. Secondly, for C++ kernels, SDAccel has native support for both arbitrary precision integers and fixed-point math type, both key in extracting maximum efficiency from FPGA accelerators. Finally, this application demonstrates the seamless support for binary swapping in SDAccel. The application reconfigures between two OpenCL binaries, one which accelerates histogram equalization to smooth the image, and a second binary which accelerates Harris corner detection. As the application runs, binary swapping is occurring when the filtering operations change. SDAccel is unique in using true partial reconfiguration for binary swapping, where the base platform portion of the FPGA remains operational throughout the swapping operation. Secondly, the base platform remains live at all times, so the DDR memory controllers stay up and the contents of the onboard DDR are preserved across kernel swaps. This completes the demonstration of SDAccel. SDAccel gives application developers a CPU-GPU-like work environment that produces efficient hardware accelerators with the best available performance per watt. Thank you for watching.